Hola, buenos días a todos. El seminario de hoy corre a cargo de Johan Knapen, de la casa. Johan se licenció en Groningen, en Holanda. Hizo su tesis aquí, en el IAC, así como su primer postdoc. Pasó otra estancia postdoctoral en Montreal. Después 10 años en Inglaterra, en Hertfordshire, que intercaló con 3 años en el ING. Y lleva con nosotros aquí en el IAC desde el 2006. Hoy nos va a hablar del Spitzer Survey of Stellar Structure in Galaxies. Así que demos la bienvenida.
Gracias, querido público. Okay, I will speak in English today, and I'll speak about this survey, the Spitzer Survey of Stellar Structure in Galaxies, which is a big survey that we started a couple of months ago. We started observing a couple of months ago. And you will see that this is also an invitation to use our data and an invitation if you want to collaborate with us. We'll be imaging 2,200 local galaxies with Spitzer, and the data will be public. So this is something to keep in mind. This is the team talk, as it were. Kartik Shet is the PI. Kartik used to be in, there's Kartik Shet. He used to be at Caltech, but he just got a job at NREO, the radio observatory in Virginia, and he's there an ALMA scientist, but he's also the PI of this survey. Most of what I will talk about today will be in this first paper that we're working on, the overview paper, which probably will not be published in 2009, but certainly should be submitted in 2009. So this is the team. The original team was 29 people, Kartik Shet as PI, and then a number of co-Is, mostly Americans, some people from Madrid, people from Finland, myself, some people from France, many people from California, Caltech, the Spitzer Institute there. And the team is growing. All these things are color-coded in some way that I can't really figure out how Kartik did this. I think where's the mouse now? Mouse is gone. It's there. It's there. But not there. It's there. Okay, good. Anyway, it's there. Yeah, I'll use that one. That one. Okay, good. Right. These, well, come on. Yeah, I'm doing that. Okay. Good. I'll point. I think that the first group of people there in red, they're the ones who will do our first stage data reduction. And they'll be on all the papers. That's the deal we have within the team. They'll do a lot of the work on the data that come in. I think the blue people are the Science Advisory Committee. The purple people, Eija Laurikainen, Heikki Salo, and Dimitri Adolfi, they're in charge of the decomposition of galaxies. So all these people are different color-coded. Then we have some people here at the end which were not part of the original proposal that we put into Spitzer. They've come in as postdocs or students, and one of those is Sebastian Comeron from here, who's working with me on his PhD. In the final year of his PhD, he will work on these Spitzer data. Several other people, and this team hopefully will grow, and there'll be more people joining us. Now, the motivation of this study is that nearby galaxies are the fossil records of galaxy evolution. That's what's left over, it's what we can see, and it's the final product also of galaxy evolution. So there's a wealth of detail that we can use to test the current models of galaxy formation and evolution. And the aim here is to create the ultimate survey of the distribution of stellar structures, the masses, and the properties of these galaxies in the nearby universe. And what we use is a Spitzer Warm Mission, which is ideal for this survey. Spitzer was launched a couple of years ago, has worked for about 3 or 4 years in the cold mode, where it was cooled, and then it observed up to about, I think, 160 micron. It's now warmed up, but has been funded, so this, I think 2 years now, has been funded by NASA, as the warm mission, so it's not cryogenically cooled anymore, and the only observations we can take are in the 3.6 and 4.5 micron bands, which is basically near infrared. So what S4G is, it's a volume limited survey, it's magnitude limited and size limited of 2,331 galaxies observed with the IRAC bands that we have available, the 3.5 and the 4.6 micron. And the exposure time per galaxy, per band, is around 240 seconds, and the whole time that was allocated to us is 637 hours and a few seconds on Spitzer. This is one of the large programs that was funded. Now here's Spitzer, 2003 it was launched, 85 centimeter mirror, so very small. Herschel's much bigger, of course. Earth trailing orbit, currently far away. It has 3 instruments, IRAC, IRS, and MIPS. IRS and MIPS are gone. They're warm, you can't use them anymore. IRAC is still working. It ran out of cryogen on 15 May 2009. And this is the call for proposals that we went for. This is exploratory science, larger than 500 hours, so really large programs. And the call apparently was made October 2008. This is a warm mission, as I said. 10 programs were awarded time, including these others, Swire, GLIM, SINGS, and S-Cosmos. I think Swire is yours, Ismail. Okay. But Ismail also has a large program on Spitzer. Doing the deeper universe. Anyway, this is one of the large programs that was awarded a lot of time on Spitzer. So what will we get? These 2 bands, near infrared bands, they're ideal tracers of the stellar mass distribution. First, they're near the radiant gene's limit of blackbody emission at temperatures higher than 2000 Kelvin, so we actually see stars. The 3.6 minus 4.5 color is basically independent of age and of the mass function of the stellar population. The effect of dust extinction is quite small in the near infrared. And for all these reasons, we really look at stars. We are not looking at gas or hot gas. We're just looking basically at old, evolved stars. And then the good point here is that Spitzer can image to extremely low stellar mass surface densities, and to levels that really are not achievable from the ground. And if they are achievable from the ground, it's a lot of effort, it's very difficult. And that is basically because the background in space is very low in the near infrared and extremely bright on Earth. So we go very deep in these images. I think B band equivalent of about 30 magnitudes per square arc second. So we really go very deep in these images. And very quick, 240 seconds per image. There are some caveats. Nothing is ideal in astronomy, so these are the caveats for using these 2 bands for what we want to do, for tracing the stellar mass. There is a very weak PAH emission feature at 3.3 micron, which has been measured by several people, and according to Tokunaga et al., this is less than 2% of the equivalent width. But it is a small feature that is sitting in our 3.6 micron band. Of course, in some regions of galaxies, or in some galaxies, there'll be more of this emission. If you have a lot of star formation, this will grow a little bit, so we have to take that into account. There is some contribution from hot dust at temperatures over 500 Kelvin, and this will contribute at 4.5 micron. And those are conditions expected only near AGN, near active galactic nuclei, or in extreme starbursts. But there is an effect of dust emission that comes in at the longer wavelength. So that's also something we have to take into account. Then there's a contamination from young red supergiants, less than 10%, but there is this level of contamination. This is serious if you want to interpret the maps that we get, the images we get, in terms of stellar mass, which is what we want. Because these young stars are very bright, so they don't have a lot of mass, but they add a lot of light to our images. So if you interpret that as a fixed mass to light ratio, you would assume that, or you would think there might be a lot of mass, but in fact there is not much mass, there's just a few of these very bright stars. So this we have to get rid of, and we're working with a small group of these people that you saw before. We're now working on a recipe to get rid of that contribution of young red supergiant. So that is it's in there. All these factors are basically similar to what we find in near-infrared. Sorry, not the first one, of course. These young red supergiants especially. It's similar as in ground-based near-infrared, but we're slightly redder. Yeah, we're at 3.6, 4.5. We're slightly redder than our standard JHK bands that we use in La Palma and other places. So we have a bit less dust extinction in the Spitzer data. So that helps. We need the combination of the two bands, the 3.6 and the 4.5. It's critical for removing the effects of the pi emission, which is only in the 3.6. There's nothing of that in the 4.5. And we also need the combination to do better modeling of the stellar light and to remove the systematics, including, we hope, these young red supergiants. We have good hope that we can get rid of those by only combining the 3.6 and 4.5. Ideally, we throw in Galax data and UV, we throw in H-alpha imaging, optical imaging, then you can really start modeling things. But for a lot of our galaxies, we won't have any other data. We'll just have the 3.6 and 4.5. So hopefully we can get rid of the supergiants just from those two bands. So that's work in progress. There's some numbers here on why space is better for this. The basic problem is this sky brightness. In the K-band, the sky brightness is about 13 magnitudes per square second, which is very, very bright. That's why it doesn't matter whether there's a full moon if you do near-infrared observing from La Palma, for instance, because the sky is already so bright that if you turn the moon on, it doesn't matter. The brightness is already ridiculous. Now, where we want to go is 13 magnitudes below this sky brightness level. And that means that we want to characterize variations down to this number. The smaller than that number is. And that from the ground is almost impossible. I've done a lot of near-infrared imaging from the ground, and we can quite easily get down to 22.5 magnitudes per square second in K, which is already 9 magnitudes below the sky. But to go that much deeper, another 3-4 magnitudes deeper, is really very, very hard. And that's where in space things get quite easy. The large surveys that are going on now on the UKIT, LSA, and the VISTA VHS. I looked up what VHS stood for yesterday. Do you know anything about it? Hemisphere survey, I think. I don't know what the V, but probably VISTA. Probably VISTA Hemisphere Survey. It's one of the big surveys. They go down to this 23 or 24 magnitude per square second, which is deep. It's seriously deep. We go another few magnitudes deeper. Go to our sample. Yes. So what we've selected is a big sample. That was the whole point of this survey. We don't want 50 galaxies or 100. We want basically all galaxies. So what we've done is select this representative sample of spiral, elliptical, and dwarf galaxies, everything. And we select galaxies with these characteristics. Nearby, so velocity less than 3,000 kilometers per second, which equates to a distance roughly within 40 megaparsec. There's a brightness limit in there, 15.5 B magnitudes as a limiting brightness. There's a size limit, basically because Spitzer pixels are 1 arc second, so we don't want to image very small galaxies. So all our galaxies are larger than 1 arc minute in B25. And then there's this criterion, which is galactic latitude larger than 30 degrees. So we avoid the galactic plane by quite a big margin, 30 degrees up and down. And we avoid everything in there because we have zodiacal light. There's emission coming from the galaxy, from the galactic plane, and we avoid that. We just want to go really deep, so we can't have that extra contribution. So what you'll find if you start looking for your own galaxies from your own samples, and you cross-correlate your sample with the Spitzer sample, there are obvious galaxies missing. And if that happens, if they're bright galaxies and big galaxies and they're missing, it's no doubt because of this criterion here, that we avoid everything that's in the galactic plane. So we end up with 2,331 galaxies, which have now all been scheduled for observation. 1,733 new targets. The other 600 or whatever are in the archive of Spitzer, and we reuse them, we recalibrate them, etc. Use them. So we've got 1,700 new galaxies coming up, and I think this is now being observed at a rate of something ridiculous, like 50 a week or so, something you can't keep up with. We find it's going very quickly. There's a lot of galaxies here. All these galaxies are either mosaicked or mapped out to 1.5 times their optical size. So that's the size that we image at. For the small galaxies, obviously, the frame is 4 arc-minutes, so we go out a bit more. But for larger galaxies, we mosaic, so we get to 1.5 times their size. 240 seconds exposure time per pixel, and then we image all galaxies down to this limit, 0.1 solar masses per parsec squared, and that equates to these numbers. And there's about 27 magnitudes per square arc second. That's how deep we go. That's at 3.6 and 4.5. And this is for all these galaxies. Yeah, this is not just a few. This is for 2,300 something galaxies, and they're all deep. You can look at all this stellar structure down to these very low levels. Total, as I said, 637.2 hours on Spitzer. So this is how the observing works. This instrument looks at the same time with its two filters. So the 3.6 looks this way and the 4.5 looks that way. And what we do, let's see, the blue one is the 3.6, I guess. So we start observing the 3.6 on the galaxy. So we point the 3.6 array on the galaxy. The 4.5 array is then looking at the background sky. And then after 240 seconds, we change and we move the telescope so that the 3.6 moves to the background and the 4.5 array moves to our galaxy. So we end up with a 4.5 and a 3.6 image of the galaxy, obviously, and we also end up with these background fields which we then use to subtract the background. It's an adjacent field of view. Scattered light from bright stars is a problem here, which we're working on. Yeah. So this is for small galaxies. This is about 4 arc-minutes field of view, if I remember correctly. So for our small galaxies, this is what we use. They just fit in one image, in one shot. So these are quick and they're very easy. The observatory loves this because they can stick in these little 10-minute observing blocks wherever they want. Yeah, you guys want to be on the field for a long time. In 10 minutes we're done with the galaxy, or 7 minutes or so. So they use this to fill up the schedule. So for them it's great, and for us it's great. These are really simple observations, and it's amazingly quick. 240 seconds, it's 4 minutes, and we're down to that ridiculous low level of surface brightness. For the big galaxies, like this one here, we mosaic. So we mosaic them with steps of 146.6 arc seconds, which has been calculated to be ideal by other people, and there's a slight offset from the galaxy center. And we make these kind of mosaics, again, of course, we're looking in different directions with the arrays, but we make sure that we get to 1.5 times the optical size of the galaxy in both the 3.6 and the 4.5 arc-minutes. So this happens for all our bigger galaxies. So that's how we observe. This is what we observe. This is the histogram of Hubble types in our survey. So here's the number, up to 400 here. And this is the Hubble type. These are some ellipticals, type -5, -3, etc. The S0s are at 0. And this goes to the very late types, type 10 and 11, which are the dwarfs and the irregulars out there. The white histogram is S4G. That's our new survey. And these two colored histograms are the local Galaxies volume survey. Forgot who the PI or the co-Is of this program were. It's under a large Spitzer program. It's 258 galaxies within 3 megaparsec, and therefore only late-type galaxies. Most of what is close to us is these late-type galaxies. So a lot of dwarfs, a lot of very late-type galaxies. That's all in the archive. Of course, we don't observe that again. We use the archive data for that. And the blue one is the rest in the archive. So that's SINGS, observed about 70 galaxies, and all the GO and GTO time. So that's guaranteed time, and it's general observer's time. So blue and green together is everything that's in the archive. So we add all the white stuff to that. Now, we need S4G to explore the full mass and morphological type space. Morphological type, you see, there are some bins like these S0s where there are very few galaxies imaged so far with Spitzer. We fill this up. Here's also this little hole, and in general, you just get loads of numbers course, within a morphological type, you then have different inclination angles, you have different parameters in mass, all kinds of parameters. I mean, there's 400 in the highest bin here. Most of there's 200 is there. So most of these bins, we have 200 galaxies per type bin. This is a histogram in mass. In stellar mass, 10 to the 9 there, 10 to the 10, 10 to 11, 10 to the 8, 10 to the 7, 10 to the 6. And most of our galaxies, because of our criteria, are around sort of 10 to the 7 to 10 to the 10 solar masses. But again, you see that we fill up, we really get a very well populated histogram. So where are these things on the sky? This is a large-scale structure from the 2-mass XSZ. This is redshift less than 0.01, so this is a local large-scale survey, the purple dots. And here, superimposed on that, are our galaxies. The red ones are the new ones, the red dots, those are our new galaxies, and the other colored ones, the blue ones and the yellow, and some other colors, they're the archive galaxies in Spitzer. So again, you see that we cover the whole sky, except obviously this whole big band in the galactic plane, which we avoid. I've talked about that. But in these regions, we have galaxies everywhere. And the interesting thing is you can identify a lot of regions which are red on the right-hand side. For instance, this whole thing here, there's a lot of red points, but there isn't any archive data. There aren't any colored points. So those are areas where Spitzer hadn't observed much before, and we will fill that in. And basically the coverage in these regions will be pretty uniform and pretty well filled up. So that's what we'll do, and of course we'll explore a range of large-scale structure with local galaxies, obviously. So just to indicate how deep we will go, this is a well-known galaxy, very well-known to some of you, 4736, which is a ring galaxy, nuclear ring in there. This is the Galax image. Now, Galax has observed a lot of galaxies. I didn't realize this until not too long ago. They've observed a lot of galaxies with Galax, and it's very, very deep in the ultraviolet. It's really very, very good data. So that's a Galax image. And there's an IRAC 3.6 micron image. This is archive data, but this is basically as deep as we go for all galaxies. Yeah. And then if you take a radial profile at 3.6 micron, which is what you see here, there's R25, which is sort of the optical size of the galaxy, 25th magnitude per square arc seconds. There's 27 down there, and you can see that we sample all that profile all the way down there. It becomes noisy, of course, if you get close to 27, but we're really going very deep. Now, this is at 3.6. In the optical bands, we're talking 30-ish magnitude per square arc second. It really is very deep. This is where the optical disk ends, and then there's all that other range that we get outside. So this is what a typical profile looks like, and of course this will get to our 2,200 galaxies. Now, what do we do as a team? Well, we have 3 pipelines that we either have in place or are setting up. I think even one isn't quite in place yet. It's being tested. This is basically what you get out of Spitzer. This is what we call a one-visit PBCD mosaic. The P stands for post, and BCD is, I think, a basic calibrated data. So this is basically what Spitzer does. This is what they give you in one visit. We look at each galaxy twice. I'll explain why. Technical reason. This is basically what you get out of them. This is our mosaic. So that's what we call our pipeline 1, where we do the combination of the data from these different visits with different roll angles. We combine those images, and we try to get the background variations out. We get a really flat background. So that's what we do. If you just go to the Spitzer archive, all our data are in there immediately. They're public. So as soon as we observe a galaxy, you can get it. You basically get, well, it's a bit extreme. They're a bit better than what you see here. But you can get all this data raw from the archive. Our data should be better, our internally reduced and calibrated data. They should be a little bit better. But if you just want to use the stuff from the archive, you don't need to collaborate with us. Use it. That's how it works. So that's our pipeline 1. That's what we do. Then we have our pipeline 2, which is basically an IRF ellipse running pipeline. So we take our galaxy, we throw in the map that shows us where the signal to noise is in our image. So white here means longer observing time in a certain pixel, and you can see, of course, that where we have little overlaps, we get higher signal to noise, and on the edges we start losing a bit. But when that goes in, these are ellipses that indicate where we get where we return to the sky level, the background sky level. I want to get these further out, but we'll be discussing that. And then we get this kind of histograms to really pin down the background level. And then what we get out is this kind of radial runs of everything. Position, angle, inclination, brightness, etc., etc. The usual stuff. If you've used ellipse in IRAP, this is what ellipse gives you. It comes out with all these parameters. And basically, that's what we do here. So we go down. This is our catalog that we'll produce a catalog down to 26.5 magnitude per square second in all cases. For some galaxies, we'll go a bit deeper, but this is the catalog number that we'll give. So instead of D25, we'll give you a D26.5, which is a new diameter, a new size of the galaxy at 3.6. That's a slightly deeper image, the 3.6, slightly deeper than 4.5. So you'll get from us in this catalog a new diameter for each galaxy. You get the position angle, the inclination, the magnitude, all the radial profiles of everything, inclination angle, position angle, magnitudes, color, whatever. And you'll also get the integrated colors in color profile. So this is going to be one of the main products of the whole survey. Eventually, we'll come up with this catalog which can give you all these numbers. The RC3 is now often used on the optical. That's old-fashioned. We're just going to do it better with these new data. So that's our pipeline 2. I have the third pipeline. The third pipeline, which will decompose all galaxies using a program called GalFit. That's the one we chose. We tried 3. GalFit is the best for our purpose. So this is what we have. We have an input galaxy, an image of a galaxy. That's our model that we make of the galaxy, and then we have a residual. And basically what we do is we model different components: bulge, disk, bar if there is one, multiple bars if there are multiple bars, lenses, ovals, and other things if we want to. There's a bit of discussion now of how many components we'll do. I think we'll end up with 4 components as standard, and then for strange cases we may do more. And this is the kind of model you get. This is magnitude here, and here's the distance in the logarithmic axis. So there's 1, 10, 100, and 1,000 arc seconds. The green component is a disk, which is an exponential disk, but because this is a double log plot, it doesn't look a straight line anymore. The bulge is this red thing sitting there. There's a nuclear ring here, which is the purple thing, and a nuclear component, because this is an AGN. So that's the kind of plots we get here and this one. The spread here is because if components become non-axisymmetric, we just basically here we plot pixels. So if you have a bar, a certain brightness level in the bar, which will be here, reaches different radial levels as you walk along the bar. That's why you get the spread in these things. So that's what we get from this from the pipeline 3. We have a workshop in December, the week before we break up for Christmas. There's a workshop here where we'll talk about pipeline 3 specifically. If anybody's interested, come and talk to me, and we have no secrets. So you can join us if you want. If you know how to do this, an expert, then you're even more welcome. So this is what we'll do again for all our galaxies, and this will be in the end. This will take a few years, but this will also be a product of our survey. We can do this. We can run these pathological cases, like a galaxy like this, and we can actually model it with GalFit. But now here, you're talking 9 components now, and we're not going to do this as standard. Because of course, if you want to do a 9-component fit, you fit everything, but what's the point if you fit that many components? But for some galaxies, we can do it, and you can see that the companion goes in here, this little area of brightness goes in there. 9 components altogether. So our pipelines can handle this. Right. So let's look at what we have. There should be a movie here. Right. Okay. This just shows you some random images of galaxies that we have. This is all from the archive. This is all archive data. We've re-reduced it. So these are images that you find. Some of these galaxies are huge. I think that was 1097. Yeah, and see how deep this is. These are big, bright galaxies. Most of these are from 6. Really good images. Background's pretty flat. They go out very far. This is just 50. These are the first 50 that we ran through pipeline 1. And it really is amazing the kind of structure that you can see here. Both within the galaxies, you look at bars and spiral arms, but especially outside where you get all this weird stuff going on outside the disk. I don't know if I recognize any of these quickly. That was an offset bar, the one we just had. Here's a client galaxy. This one will come back later, the Hadron Galaxy. I'll show that later. Sebastian's doing some work on this. M51 is coming up. This is 4321. There's M51. There's M51. A lot of these galaxies you will know, but you may not even recognize them on these images because they're so different. Like M51, there's all this stuff around the companion, which is just very deep imaging. You see this. So this is basically, it's not quite random because these are bright galaxies, mostly big SINGS galaxies. But this is what we get, and this is what we'll have 2,300 times. Yeah? So it's all there. This is all in the archive. You could have used this by now for years. It's all there. This is some of our new data. So just to show you that it's coming. It's not as nice yet. We haven't done all the processing yet. But this is the Warm Mission data. Right? There's always been a question, of course, if you really start using the Warm Mission, is the data going to be as good as it was in the cold mission? Because your camera is warm, your telescope's warm. And the answer is yes, it is as good. So these are some galaxies that we observed. This is part of S4G. And these are galaxies that are coming. This is what's coming out of the telescope now. So what are we going to do with this? I'm just going to give you some examples from the science case that we put in the proposal. One obvious thing to look at, of course, is the outskirts of galaxies. This is a topic that's well known in this institution. A lot of work has been done and is still being done here. This is looking at the nature and the frequency of complex disk profiles, and what we'll produce is basically a catalog of disk breaks. This is a single exponential profile, so this is radius here versus surface brightness, and there's an exponential disk. Exponential, it becomes a straight line, of course, if you plot this with one logarithmic axis. This is an ongoing single exponential all the way down. This is a break, this is a truncation, and that's what Poland and collaborators called an anti-truncation. So this is a change of slope in the exponential profile in the disk. Right, what are our advantages? Well, our advantage obviously is that we go very far, 1.5 times the radius of the galaxy, and ridiculously deep. So we'll be able to do this and just look at all our disk galaxies that we have in the sample, hundreds, not quite thousands, but on the disks we get close to 2,000 galaxies. So we can do this. This is one of the obvious things that we look at. Another obvious thing you've already seen is in the images is this whole issue of tidal features and tidal debris, stuff that's hanging outside galaxies as a leftover of past interactions or current interactions. And one of the things to look at then is a correlation to AGN and starburst activity. We've seen, again, beautiful pictures from in this institution. David and Ignacio have published these very deep optical images of galaxies where you see this weird tidal stuff very beautifully around galaxies. That's great. Individual cases, we'll be able to do that statistically. We'll get a few hundred of those cases, maybe, I don't know. We'll find out how many we'll find. And then we can do things like correlating this to AGN activity, starburst activity, to how busy the field around the galaxies is, look at interaction rates and companions, etc., etc., etc. So here are some examples. That's an elliptical, I think. You can look at shells and elliptical galaxies, which may be leftovers from dry mergers. Look at differences in clusters versus the field. Look at lopsidedness and shapes of galaxies. You may have noticed one galaxy where the whole bar is displaced from the center. In the galaxy, the disk is round and the bar is sitting not quite in the middle. It's sitting on the side. Why is that? If you go further out, we'll look at lopsidedness and shapes. A lot of this stuff has been seen. In fact, all of this, shells are well known. They exist in ellipticals. Lopsidedness is well known, especially in H1. But again, we'll be able to throw the statistics on there, get this for a few hundred cases, and then see why in certain cases we see this and why in other cases we may not see it or may see it differently. Then we look at the components. We look at bulges. We can look at bulge size, mass, and shapes. Again, because we're looking at the old stars, we get all these parameters, and we do this precise decomposition. So we get to the full complexities of the bulge types. These are some more modeling examples of this galaxy. It turns out if you want to do a bulge disk decomposition, you have to take into account the light from the bar and the lenses, for instance. If not, your numbers can become less reliable. But that's what we will do as our pipeline 3, our Gulfit pipeline that I described to you. We'll do that, and again, we'll do that for hundreds of galaxies. So we'll look at bulges, and again, bulges along the whole sequence of morphological types. And we have elliptical galaxies in there as well, of course, that we'll compare with. Then we go to this. Oh, there we go. Oh, we've seen this. Right, bars. We look at bars, which are signposts of galaxy evolution. The fraction of barred galaxies declines from about 60% locally to under 20% at a redshift of 1. This is Kartik-Shet's result. There are other results in the literature, but it seems to be the most up-to-date. This is still under debate. Yeah? And we'll certainly, what we'll pin down, we won't go out to a redshift of 1, but we'll pin down the bar fraction and the bar properties at a redshift of 0, where we are now. This bar fraction depends on the host galaxy mass, it depends on color, it depends on bulge properties, and that will all sort out. I'll skip all these diagrams, you can find them in the literature. So here are some barred galaxies from these are Spitzer images, obviously. And what we'll look here, we'll make the sensors of local bars. We'll look at bar frequency, bar length, bar strength. We'll look at nuclear bars. We'll look at lenses, and then we correlate this with rings and spiral arms. And of course, we look at all these bar properties as a function of galaxy properties. And from our pipelines, we have all this information. We have the inclination, the angle, position, angles, all the different components. We have the disk, we have the bulge, we have the relative ratios, we have everything. So do this for a few hundred galaxies or a few thousand galaxies, and you'll know more about bars. Some other things, we look at ellipticals and lenticulars as a class. We have about 150 of those. So they're also in the sample. We look at the dwarfs. There's more than 135 dwarfs. Of which 87 DDO dwarfs, they're also in the samples. We look at dwarf galaxies. Adjon systems, we have about 350 or more of those. We can look at these questions like bulgeless galaxies, vertical scale height, I'll come back to that in a minute. Then we look at Tully-Fisher relation, we look at the fundamental plane. We can look at energy sources for heating the dust in the outer disk, look at interaction and merger fraction, independent measure of AGN activity, look at AGN physics, and many more things. And other ideas from within our team and the whole community. This is something that we want everybody to use. So any other ideas you have, please use this data. Whether you work with us or not, we don't really care. The ultimate goal is to create the ultimate survey of the distribution of stellar structures, their masses and their properties in a nearby universe. That's what you'll get from us. It will take a few years to do that. Team policy, data products and jobs, etc. The usual stuff. The important point is that everyone in the community is welcome to work with us. This team policy that we have a document that's modeled after the Cosmos team, with Nick Scoville there, and that is regarded as being very successful, very open. You see how many papers have come out of Cosmos. It's frightening. There's a lot of stuff going on. Partly because they've been so open, and we want to do that as well. So we invite everybody, and certainly people here, of course, because I'm here, so I'd love to work with people here, or even if you don't want to work with me, just use it anyway. We want the community to work with these data and get signs out. This is what you get from the archive. S18.7, IRAC, reduced data. They're expected to be pretty good, and they're released immediately. Yeah, immediately, for days. Takes weeks or so. So you can look at the Spitzer websites and find out when our galaxies are being observed, and you just grab them from the archive and write papers. And fantastic, fine. If you collaborate with us, good, better. Yeah, but you can get these data. This is what you'll get, pipeline 18.7 from IRAC, and that's pretty good. Yeah, that's usable. You can certainly write papers on it. There's absolutely no problem. It's calibrated, it's fully reduced. You can use it. We'll do this additional processing of data and release that roughly every 9 months after acquisition of data. We'll see how that goes, because we've got to run it through our own pipeline. If you want to use our data, you'll have to collaborate with us. Yeah, if you really want our data products, then of course you collaborate with us, or you wait. You work on the science, hopefully. That's how it works. Ultimately, we'll get what I described as full catalog with all the parameters, very much like the RC3, and all the structural measurements, and then you're talking 2012, 2013. Then we'll hope to get this whole catalog finished. So that will take some time. We expect to hire 1 or 2 postdocs and 1 or 2 grad students immediately. There is an advert out at the moment for a postdoc to work at in Charlottesville with Kartik Chet on this stuff. I think the deadline is the end of the month. So that's for a postdoc position specifically to work on S4G. Right. Now, a bit on the ISC involvement, what basically I do and Sebastian is involved at the moment. We've got at the moment the lead on the H-alpha follow-up, which isn't really a follow-up because it's only archival data. We're not going to observe 2,000 galaxies in H-alpha. But if you look through the literature, we find about 600 or 700 galaxies that actually have a usable calibrated H-alpha images out there. So we're collecting those for use in the team. We're leading the study of ringed galaxies. That is part of the last year of Sebastian's thesis. I'll coordinate an EU ITN proposal, which we have to write basically within a month now to get postdocs and grad students and a network set up within Europe. There's about 6 or 7 Europeans on S4G, so we'll try and get this network done. So that's what will happen here. There's this Pipeline 3 workshop in December that I already mentioned. We're looking at vertical structure of galaxies and a whole variety of other science issues. And if you want to talk to me or Sebastian, please feel free and welcome. There's so many things we can do with this data, either with individual galaxies, a few galaxies, or with the whole sample. Please come and talk to me. I'll give you, finally, a little, these are slides that Sebastian prepared. It's what he's been doing This is what we're doing at the moment within the IAC. We're looking at resonance features in S4G, resonance features rings, inner rings, outer rings, and nuclear rings. These resonance features appear in the literature. We find them from the literature, and then we look at images to confirm that they're actually real. So that's been done. And this number is likely to increase because we either confirm more rings in the literature. There's 50 cases that we haven't really been able to confirm yet, and we may find new rings. And of these galaxies, these 2,331 galaxies, 89 have outer rings or pseudo rings, 136 have inner rings, and 59 have nuclear rings. And this is great. These numbers are fantastic because you can really start to do statistics on them. To really measure, what we want to do is measure the properties of the rings and then correlate those ring properties with the galaxy properties. Any properties we can get our hands on. And with these numbers, you can really start doing statistics on them. And that's not been done before. There's been attempts in the literature, but no one has ever had this kind of data set to work with. Right, so that's the last chapter of Sebastian's thesis. And this is something that he's been working on recently. This is a profile of the Edge-on galaxy 4244, which you see here in a histogram equalized display. You've seen this before in the movie. Here, this really brings out all the gory stuff in the background, and you see what the problem we have is masking out stuff in the background, stars or galaxies. But if you look at the vertical profile, so if you go out within this bin, you average everything, you go out from the disk up and down against some, you get this profile. You start out here, this is a nice, this is the exponential disk. Basically, it's an exponential, because it's a vertical, it's not a exponential disk, it's a vertical distribution. That's an exponential. This is sort of the level where things get a bit hairy, so this is now down at 28. deeper than I said before because we're averaging all these pixels up together. Yeah, we take this whole big band. Going down to 28. And this little area here was enhanced emission. I think that is the thick disk. Thick disks are everywhere in galaxies. They've been found in many galaxies, but not in this one. When we started looking at this one, we didn't realize that this was the only edge-on galaxy without a confirmed thick disk, so when we couldn't find it, we got a bit annoyed. It turns out that this is the one out of 20 or 30 where people have not been able to find thick disks. But I think it's there, it's just very faint. I think it's this extra component, this change in slope there. I think that's the thick disk. So that's in progress. It's just one image that we got. This was in the archive, this image. We just got it from our pipeline one and are doing stuff. And hopefully with time we'll have the chance to look at more of these edge-on galaxies. So that's all I wanted to say. And again, I want to reiterate, please use the data. If you don't want to talk to me or Sebastian, I couldn't imagine you wouldn't want to talk to me. But go ahead anyway, use this data. It's going to be in the archive. But we welcome collaborations on any idea you may have. If there are conflicts, of course, with people in the team, then we'll sort them out. But there's so many things to do with this data, so please go ahead and do science.
So we have some time for questions and comments. Anybody?
Johan, compared to the SINGS data, are these data... Compared to the SINGS data, the new data are comparable in depth or...
I don't know the exact numbers, but I think they're comparable. Yeah.
Anybody else?
Right. I think that's sort of a natural limit if you observe with IREF. If you go much deeper, then these background stars will get you. It's going to be a mess. Right.
That's okay.
Do you have the list of objects on the website?
Yes, I think.
And the ones already observed, or the plans for release?
I think for that you'll have to go into the Spitzer observatory pages. But all this stuff is public. I forgot to say, one of the things we'll do here, we'll host the project web pages here as well. Jorge is making them, I hope, at the moment. So we'll have the web page, and one of the things I'm insisting on is that we get a searchable table of our sample. So you can see the table and you can say, I want everything in inclination more than 70 degrees and closer than this and type later than 7. And then all the galaxies come up as little images and click on them. So that's something that we'll host here. But yeah, all this stuff should all be public. I don't know how to find out which galaxies have been observed, but it's there. It's all on the observatory pages. If you can't find anything, let me know. I'll send an email to someone.
Nobody else? Okay, I have a question. Have you come across any regular galaxy? What do you do with them? Do you try to